I would like to show you a little bit more in terms of what you can achieve with the results of the dynamic simulation or the Invent itself. Invent and Nastran, it's actually a way more powerful tool than the inbuilt simulation in Inventor, because it opens up lots of opportunities for you to access very high-end analysis types such as explicit. I decided to see what's the force required to break this boom. You know, this is the case when we need to account for the abuse load by the end users. And the easiest way to do it is to do the mechanical event simulation using Invent and Nastran, and particularly the explicit analysis. What I did, I took this model here and I defined some basic constraints. So it's like I enable some rotation, kind of realistic constraint on those bolted connections here and there. So just fix those two parts, made them static, of course, taking into account the actual angles of those constraints. And this is what I obtained from the dynamic simulation. And then I applied 100 millimeters enforced motion or imposed motion on this lug. So let's have a look at the force. I am interested in the hydraulic cylinder load. And this load, it comes from the reaction force at this point here. So let's have a look. So I'm going to create a new plot, point to this node here, and then plot results from time 0, that's my starting point, so no load, to the time 1, which means end of my simulation. So the result I'm looking for is reaction force, the total value. As you can see, it has just 1 degree of freedom fixed, so then the total value will give us the actual value on that constraint. So let's have a look. So yep, that's the plot. The plot looks pretty realistic because I used non-linear material here. It's the it's mild steel 1020 with 350 megapascals yield stress and 400 and something megapascals ultimate stress. So anyway, we can take a look at the results here. Yes, 420 megapascals ultimate stress with the maximum elongation at break 15%. So this non-linear material model enabled the actual reaction force required to bend this stuff. And as you can imagine, the reaction force is non-linear because at some point we are experiencing plastic deformations in the most critical part. And that's why the responsiveness of the whole model towards this enforced motion becomes different. So the model becomes softer due to the formation of the plastic joint in the place where we have the maximum bending moment. So that's why at some point we have linear connection between the applied load in millimeters. So 10 means 100 millimeters up until the change in the behavior when very insignificant increase in load leads to dramatic deformations in the model. So in terms of the stress capacity of the part, what we can conclude from it? As you can see, up until like the 120 kilonewtons on this side, up until this point, we don't experience any pretty much like plastic deformation, so it's linear connection. We can make some research in detail to find that the weakest spots, but it's just completely okay to run within those limits. But around this point here, which is 150 kilonewtons, the situation changes dramatically. And as you can see, from if we increase or the load or go beyond 150 kilonewtons, the model deformations increase really seriously. So the probably maximum we can get out of this model is about 1.8, 180 kilonewtons. And after this, it's going to collapse because the model becomes so soft, the plastic joint increases so dramatically. So it's just like the maximum it can take. So let's have a look at the plots to find out where are the problems and what are the possible ways to improve this model. So first thing is, it's the stress. So unfortunately, we don't have the equivalent stress available in those results. And that's why we need to be careful with von Mises stress. As you know, it doesn't work beyond the yield point. So the results, the maximums that we're going to get in the von Mises are not quite right. But all the way before yield, it's just perfectly fine. So that's why we are going to determine the areas affected by the yield stress. So what I'm going to do, I'm going to set my maximum to 350 megapascals, set deformation as actual, so it's 100% scale, 1-to-1, and then just display the results. So that's what I expected. All these red areas are affected by the plastic deformations. The maximum is here. And even with the von Mises stress, it's not exceeding the maximum stress, which is 420 megapascals, which confirms that the model is still operational, but it's very close to the complete collapse. In some areas, the plastic deformations significantly affect the welds. And in this model, the welds are presented as just some small pieces of material using the shell elements. That's why those welded connections, they might need some extra analysis later, but at this stage, it's okay just to understand where are the weak spots. The next bit is we can analyze strain and see the actual areas dramatically affected by the plastic deformations. And as you remember, the maximum we can get is 0.15, so 15% before it breaks. It seems like that there are no areas in the model where we have stresses higher than that. Plus, I specified the element deletion criteria, so it will actually break if we exceed the maximum stress. However, it didn't happen. Models like this, they can give you pretty good understanding of your concept. You can find out the areas affected by the plastic deformation. If you understand that despite of some imperfections in the model, it can withstand way higher loads than actually designed.